In this chapter, we are going to look at how we can fabricate metal alloys based on their application. Okay, but before that, we need to classify different types of metal alloys. As you can see from this slide, metal alloys can be divided into two categories, which are ferrous metal alloys and non-ferrous metal alloys. Ferrous metal alloys are those in which iron is the base or the main constituent, including steels and cast iron. Okay, steels and cast iron. While non-ferrous alloys are those alloys that are not from iron based. Ferrous alloys are produced in larger quantities as compared to the non-ferrous alloys. Okay, this is the reason why ferrous alloys are produced in a larger quantities because iron containing compounds. Okay, ferrous, as we know, it made up of the iron as the base principle, as the base or main constituent. Iron itself exists in abundant quantities, so we can extract iron from the earth crust. Okay, the second reason why ferrous alloys are produced in larger quantities is because the production or it is more economic, cheaper to produce the iron based material as compared to other materials. And the third reason is because they are extremely versatile, meaning that they may be tailored to have a wide range of mechanical and physical properties. Okay, with this kind of these three main reason made up why ferrous alloys are mostly used and produced in a large quantity. However, the main disadvantage of many ferrous alloys is their susceptibility to corrosion. Okay, because they are ferrous iron based, so they are susceptible to corrosion. Steel or iron carbon alloys. Okay, this steel is also known as iron carbon alloys, and it also contains other elements of alloy such as copper, zinc. So they are made up of the main constituent is iron, followed with carbon, which is normally less than 1.4 weight% of carbon, and also they have another constituent such as zinc, copper, depending on the application of the steels. Okay, while cast iron contain about 3 to 4.5 weight% of carbon. So as we compare between these two, okay, cast iron normally they have a lower melting point, okay, as compared to the steel, and therefore cast iron easily melted and easy to be casting. Okay, and therefore some cast iron are very brittle, and casting is the most convenient fabrication technique. Metal alloys can be fabricated via various techniques. Okay, the classification of metal fabrication techniques include various metal forming methods such as forging, rolling, extrusion, and drawing. And the second technique is casting, and other techniques such as powder metallurgy and welding. Normally, two or more of these must be used. Okay, combine two or more of these methods before the final metal alloy product is produced. The methods chosen is depend on several factors, and the important factors, properties of the important factors that must be considered are the properties of the metal, okay, the size and the shape of the finished metal product, and of course the cost. If the metal is experience forming operation, or if we apply forming operation to the metal, either one of these, forging, rolling, extrusion or drawing, the shape of the metal piece is changed by plastic deformation, and this plastic deformation is induced or is due to the external stress. Okay, this external stress of course must exceed the yield strength of the metal so that the plastic deformation will occur. Okay, metal must be at least moderately ductile so that it can go plastic deformation, and capable of some permanent deformation without cracking or fracturing. While for casting technique, these techniques are used if we want to produce finished shape is large or complicated, meaning that the product of the metal alloy has a large shape, and the shape is also complicated, so that we can choose casting technique. Or if the alloy used is very low in ductility, where we cannot use forming operation or powder metallurgy or welding, so that casting is used. And most importantly, casting is the most economical as compared to the other techniques. For forming operations, we can conduct this under two different temperatures, either hot working operation or cold working operation. For hot working operation, deformation of the metal alloys occurs above recrystallization temperature, and while cold working operation, the deformation occurs below recrystallization temperature. Cold working operations normally conducted at room temperature. For hot working operation, it will induce large deformation, while cold working it will only induce a small deformation. And if we compare in terms of the finished product, hot working operation will normally experience surface oxidation. Okay, and due to this, material of the metal will have experience some loss of material, and the final product is the surface finish of the final product is not really good. While for cold working operation, it will produce metal alloy with increased strength, and the quality of the surface finish is much better as compared to the hot working operation. And of course, mechanical properties is much better than the hot working operation. However, for cold working, it is much expensive, and the procedure is also quite inconvenient. The four different forming operations when we do the metal fabrication, okay, are shown in this slide. Okay, forging, rolling, drawing, and extrusion. Okay, each of these are different in terms of their process. Okay, for forging operation is mechanically working. Deformation, a single piece of normally it can be done under hot or cold forging. Okay, a wide range of metals can be forged. Typical metals used in forging include carbon steel, alloy steel, and stainless steel. Okay, however, some soft metals such as aluminium, brass, and copper can also be forged. The forging process can produce parts with excellent mechanical properties with minimum waste. Okay, normally wrenches, crankshafts are produced using forging method. Rolling is the most widely used deformation process. It can be also conducted under hot or cold rolling. It consists of passing a piece of metal between two rolls. Okay, two rolls, and we pass through the metal, and this will produce a reduction in thickness of the metal. Okay, because we expose this metal to the compressive stress exerted by these two rules. Cold rolling may be used in the production of sheet, strip, and fall with high quality surface finish. Drawing method is where the metal piece is pulled through dies, okay, by means of tensile force applied on the exit side. This will cause a reduction in cross-sectional area with correspond to the increase in length. Okay, we increase the length and reduce the cross-sectional area. Okay. Drawing normally used to produce rods, wire, and tubing. For extrusion, a bar metal, okay, is forced through a die by a compressive force that is applied to a ram. Okay, a ram here, and we apply compressive force to the metal through a die. The extruded piece that emerge has the desired shape and a reduce in cross-sectional area. Okay, these extrusion products include rods and tubing that have complicated cross-sectional geometries. So if you want to produce rods or tubing that have complicated or complex cross-sectional geometry, we can use this extrusion method. Casting is a fabrication process whereby a totally molten metal is put into a mold cavity having the desired shape. Once the molten metal solidified, the metal will follow the shape of the mold with a little bit shrinkage of the size. A number of different casting techniques are commonly employed, including sand casting, die casting, investment casting, and continuous casting. Sand casting is the most common method used, where we can only use ordinary sand as the mold material. Okay. A two-piece mold is formed by packing sand around a pattern that has the shape of the intended casting. Sand casting is normally used to produce large materials or large parts, such as automotive cylinder block, fire hydrants, and large pipe fittings. The second method of casting, we call it as investment casting. Okay. This investment casting, where the pattern is made from a wax or plastic that has a low melting temperature. Okay, that is the first step. Around the pattern is put a fluid slurry, which is set up to form a solid mold, or we call it as investment. Okay, here, plaster of Paris or high-grade ceramic slurry is usually used. Okay. The mold is then heated such the pattern melts and is burned out, leaving behind a mold cavity having the desired shape. Okay. This technique is employed when high dimensional accuracy, reproduction of fine detail, and excellent finish are required. Okay, those are the requirement. If we require those kind of properties, we need to use this investment casting. In die casting, the liquid metal is forced into a mold under pressure and at a relatively high velocity and allowed to solidify with the pressure maintained. a two-piece permanent steel mold is employed. Okay, when clamped together, the two pieces form the desired shape. When complete solidification has achieved, the die piece or the mold are open and the cast piece is ejected. For continuous casting, which is also known as strand casting, is the process where a metal is heated until it liquefies. Okay. The molten metal is then allowed to solidify until it becomes a semi-finished slab that is later rolled in the finishing mill. In this process, the molten metal is continuously supplied to the mold, so that we call it as continuous. When the molten metal is cast through a mold, it keeps traveling downwards, increasing in its length as the time passes by. The molten metal is continuously passed through the mold at the same rate to match the solidifying casting. Okay, this results in casting of long strands of metal. So that's why it is used to produce rectangular slabs or cylinders. Powder metallurgy involves the compaction of powdered metal, followed by a heat treatment to produce a more dense material. This method is especially suitable for metals having low ductilities, since only small plastic deformation of the powder particles need to occur. In welding, two or more metal parts are joined to form a single piece. When one part fabrication is expensive or inconvenient. So if the other fabrication technique is unavailable or expensive, we can opt to do welding technique. In welding technique, the workpiece to be joined and the filler material, or you call it also as welding rod, both are heated to a high temperature to cause both to melt. Okay, once solidified, the filler material forms a joint between the workpiece. Okay, there is a region adjacent to the weld that may have experienced microconstructural and property alteration, and we call this region as heat affected zone. Metals are used as they have an electrical properties. If you look at this slide, this is focusing on integrated circuit, or we call it as IC, which is used in almost all electronic equipment. IC is a set of electronic circuits of one small flat piece, or we call it as chip. Okay, if you could look at this is considered as a piece of chip. Okay, and it is a semiconductor material, usually made up of silicon. Okay, large numbers of tiny metal semiconductor, in this case aluminium is used. Okay, these aluminium are integrated into this small chip, and this clearly that silicon act as the base material and aluminium as the conductive material. One of the most important electrical characteristics of a solid material is the ease with which it transmits an electric current. Okay, we can use Ohm's law that relates the current I, or the time rate of charge passage, to the applied voltage, or V. Okay, and we represent this using this equation, where R here is the resistance of the material. Okay, so this is the Ohm's law. V equal to I, current, multiplied with the resistance. Okay, the R value is dependent on the resistivity or rho. Okay, with this expression, okay, rho equal to R, which is the resistance, multiplied with A, cross-sectional area of the current flow, divided with current flow path length L. Okay, so if you can look at this image, so this is the length of the material, A is the cross-sectional area, and R is the resistance or ohms. Okay, sometimes electrical conductivity or sigma is also used to specify the electrical character of a material. Okay, this is quite straightforward. It is simply the reciprocal of the resistivity, 1 over rho. Materials with good conductivity and resistivity values are used in electronic devices. And these two values, conductivity and resistivity, are also geometry independent, meaning that conductivity and resistivity of material are independent of the size or shape of the material. This means a thin copper wire in your computer has the same conductivity and resistivity as your grandmother's copper vase. Okay, pasu tembaga parents you tu, atau whatever copper material in your house. Okay, they have the same values of conductivity and resistivity as the thin copper wire. For metals, the resistivity is increased by 3 ways. Okay, the first one is increasing temperature. If we increase the temperature, meaning that the resistivity or thermal resistivity of a material is also increased. This is due to the vibration, thermal vibration of the metals that induce the increasing in resistivity. The second one is with addition of impurities. Increasing the for example, if we increase the concentration of nickel as the impurity in the copper, this will result in the enhancement of resistivity. And the third one is plastic deformation. Okay, plastic deformation raises the electrical resistivity or increase the electrical resistivity as a result of increased number of electron scattering dislocations. Okay, however, this plastic deformation is this factor is much weaker than that of increasing temperature and the presence of impurities. Next is the application of metals in thermal material, okay, as a thermal material. Okay. A solid material, when it is heated, it will experience increase in temperature. Okay. That because of the energy has been absorbed. Okay. One of the property that we can measure is heat capacity. Okay. Heat capacity is a property that is indicative of a material's ability to absorb heat from the external surroundings, and it represents the amount of energy required to produce a unit 1 degree temperature rise. Okay, or we can represent this in the mathematical equation here. Okay, heat capacity C delta Q, change in energy input, divided with the change in temperature. And the unit for heat capacity is joule per mole per Kelvin. Okay, there are two ways to measure heat capacities. Cp and Cv. Cp is heat capacity at constant pressure and Cv is heat capacity at constant volume. If we look at this list of materials and their heat capacity, specific heat capacity values at constant pressure, Cp, the groups can be divided into polymers, ceramics and metals. And as we can see, metals has the lowest value of Cp as compared to polymers. Okay, so why is Cp significantly larger for polymers? So we can describe this by looking at the density of the materials. Okay, polymer is much less dense than metal. Okay, it's less dense than the metal. We know that metals are made up of a closed packed structures where atoms are tightly bonded to each other through metallic bonding. While in polymer, molecules can be very long molecule and branched in shape. Okay, meaning that they cannot fit or they cannot bind tightly together very well. They are therefore not as close packed. Okay, polymer not as closely packed as compared to the metals. So that's why much energy is required to raise 1 degree temperature, 1 degree Kelvin temperature per mole of each materials. Okay, so that's why the value is higher. Energy is required is much higher than the metal with much more dense in terms of their atomic structure. Apart from heat capacity, materials also experience thermal expansion. Okay, materials will change in size when the temperature is changed. Most solid materials expand when we heat up the material, and when we cool the material, it will contract. The change in length with temperature for a solid material can be expressed as this equation. Change in length, final length minus delta length. Final length minus with initial length divided with initial length is equal to the alpha L, which is linear coefficient of thermal expansion, divided with the change in temperature, final temperature minus initial temperature. From an atomic perspective, if we look at in atomic view, okay, thermal expansion is reflected by an increase in the average distance between the atoms. Okay. This phenomenon can be understood by looking at this curve or looking at this graph. Okay, the potential energy axis versus interatomic distance. Okay, the distance between atom. Okay, and this one is a asymmetric curve. Okay, the curve is not symmetric. If we look at this curve, heating the material to a higher temperature, let's say from temperature 1, temperature 2, temperature 3, will raise the vibrational energy from E1 to E2 to E3 and so on. Okay, so T1 will increase the temperature to the vibrational energy E1, increase to T2, the vibrational energy also will increase to E2 and so on. The average interatomic distance is represented by the mean position, which means increase with temperature from R0 to R1, R2, R3 and so on. Okay, as we increase the temperature, so the mean distance between atom also will increase, R1 to R2 to R3 and so on. Okay. if let's say the potential energy is the curve symmetric. Okay, if the curve is symmetric as shown in this graph, okay, the same curve, potential energy versus with interatomic distance, okay, the distance between atom, okay, this form the symmetric curve. Okay, if we can see from this, the change in temperature, okay, from T1 to T2 to T3, and obviously it will also increase the vibrational energy from E1, E2 to E3. There will be no net change in interatomic separation. Okay, they will cancel out each other, and consequently there will be no thermal expansion. For each class of materials, metals, ceramics, polymers, the greater the atomic bonding energy, the deeper and more narrow potential energy curve. As a result, the increase in interatomic separation with a given rise in temperature will be lower, okay, and yielding a small value of alpha L, or this linear coefficient of thermal expansion. So clearly from these values, polymers, metals and ceramics, we can see ceramics has a low value of a linear coefficient of thermal expansion after alpha L as compared to polymers. Okay, this is because polymers have weak intermolecular bonds as compared to ceramics and metals. Okay, because of these weak intermolecular bonds, so the molecules are far apart from each other. Okay, the molecules they are not close packed to each other, and they are far apart from each other. And adding heat to these molecules make them go further apart. Okay, become lagi jauh lah. Okay, atom tu lagi jauh, and that's why polymers have low melting point as compared to metals and ceramic. Okay, because their intermolecular bonds are weak and far away from each other. Okay, while metals and ceramic, they are strongly bonded. Okay, we know that ceramic they are bound to each other by ionic or covalent bond, and metals are binding together via metallic bonds. Okay, and this strong bond between atoms and molecules make them the bonds are less easily opened by heat. Okay, because they are close to each other. Okay, they are not keen to the heat, just like those bonds are easily stretched by pulling in tension. So that's why metals and ceramic have high melting points as compared to polymer. Next thermal properties of a material is thermal conductivity. Okay, thermal conductivity is the phenomenon by which heat is transported from high to low temperature regions of a material. Okay, the property that characterizes the ability of material to transfer heat, we call it as thermal conductivity. And we can use this equation known as Fourier's law to express the thermal conductivity. Q, heat influx, is equal to negative K, thermal conductivity. dt over dx is the temperature gradient through the conducting medium. If you can imagine in terms of atomic point of view, okay, the atomic vibrations and free electrons in hotter regions, okay, let's say this area have hotter high temperature region, and atomic vibration and free electrons in this area will transport energy to the cooler regions. If we compare the conductivity of materials between metals, ceramics and polymers, Metals show a very high thermal conductivity as compared to ceramic and polymers. Because metals, they are very good in conducting thermal or heat because of two reasons. First, heat transport is much efficient because electrons are not as easily scattered. Because they are bound together via metallic bonds, and the electrons are not easily scattered, and they have high velocities. The speeds, the velocities is very high. And the second reason is because metals have relatively high or large numbers of free electrons, that participate in thermal conduction. But in ceramic, they are normally behave as thermal insulators. They are not thermal conductive, but they behave as thermal insulators because they have lack of numbers of free electron. Metals, they have large number of free electron, but for ceramic, they have very small amount of, sometimes very little amount of free electrons. And the transfer of energy is purely from the atomic vibrations. The atoms itself vibrate. While for polymers, energy transfer is accomplished by the vibration and rotation of the chain molecules. We know polymers are connected to each other by a long chain. The magnitude of the thermal conductivity depends on the degree of crystallinity. If the polymer is highly crystalline and ordered structure, they will have higher value of thermal conductivity than the amorphous polymer. So that's why polymers are also often used as thermal insulators, because they have low thermal conductivity value. Magnetism is the phenomenon by which materials have an attractive or repulsive force on other materials. Many of our modern technological devices rely on magnetism and magnetic materials, including electrical power generators, radio, television, telephones, and computers. Iron is a well-known example of a material that exhibits magnetic properties. Magnetic forces are generated by moving electrical charge particles, or I current. The magnetic flux density, or also known as B, or magnetic induction inside the material, can be calculated by using this equation. This magnetic induction inside the material is always in the unit of Tesla. So we can calculate them based on the permeability of a solid. This depends on the type of solid, which is mu value, multiply with H, where H is the magnetic field strength. How much is the magnetic field is applied to the material. Several parameters can be used to describe the magnetic properties of a solid. One of these is the ratio of permeability in a material to the permeability in a vacuum, or can be represented by this equation. The ratio of permeability in material divided to the permeability of a vacuum, and this permeability value in a vacuum is equal to this value, 4 pi times 10 power to negative 7, or 1.26 times power to 10 power to negative 6 Henry per meter, H over m. Because this value is H over m, and permeability of a solid is also H over m, So the ratio of permeability is dimensionless or unitless, that it has no unit. Another field quantity is M, or we call this as magnetization. Okay, the magnetization of a solid is proportional to the applied field as given by this equation. M, magnetization, is equal to magnetic susceptibility, which is it has no unit, multiplied with the H, which is the magnetic field strength. Let's say we have both combination of magnetization and H, which is the magnetic field strength. Okay, H and M present. So the value of B, which is the value of Tesla, is given by this equation. Okay, we combine both. Okay, B is equal to permeability of a vacuum with H, which is magnetic field strength, plus with the permeability of a vacuum with the magnetization. And since we have the magnetization formula is this, so we can substitute the M value here with this formula, given us this equation. Okay, so B equal to the H term, which is from the magnetic field strength, and from the magnetization values. Okay, contribution from the magnetization. So B can comes from two parameters. One is H, which is magnetic field strength, this term, and another one is the magnetization. Okay, this will contribute to the alignment of the field. Okay, so we apply the magnetization, or we apply the magnetic field. Okay, the material will align with the field. Okay, in terms of this equation. Okay, these two equation here. So this one we rearrange, forming this final equation. The magnetic properties of a material is the consequence of magnetic moments associated with individual electrons. Okay, each individual electrons react to the magnetic moment applied to it. Okay, so we can visualize this individual electron motion by looking at these two images here. Okay, first we can say that each electron in an atom, one is related to its the motion of electron is related to its orbital motion around the nucleus. So this is our nucleus, this is our electron. It will move around the nucleus, okay, and being a moving charge, an electron may be considered to be a small current loop, okay, generating a very small magnetic field. So this is our direction of magnetic field. Okay, it will move, electron will move around the nucleus and producing or generating a magnetic field. Okay, and this having a magnetic moment along its axis of rotation. So we can visualize, we have nucleus, we have electron moving around the nucleus, and this motion producing the magnetic moment along its rotation. Okay, as you can see from this image. Okay, electron is also producing a magnetic moment from the spinning around the axis. Okay, the electron also is considered or is assumed of as spinning around an axis. Okay, which is directed along the spin axis. Okay, so this is the spin axis. Okay, the electron cloud spinning around, along this spinning axis. Okay, the electron is spinning. So this is the direction of spinning. Okay, our electron are moving along this spin axis, and this also will produce magnetic moments. And the net atomic magnetic moment, or the total atomic moment, is the sum of these two motion. Okay, and from this, the motion of this electron, it will produce 4 types of response. The 4 response of the magnetism, which are diamagnetic, paramagnetic, ferrimagnetic, and ferromagnetic. Okay, so we look at diamagnetic with the magnetic susceptibility, or the Xm value, is about 10 power to -5, which is indicate that this is a low magnetic susceptibility. These are the example of materials that are having low degree of a material can be magnetized in a magnetic field. Okay, these are the example of material that responds to the magnetic field in a very low value of magnetism. Okay, followed with paramagnetic, with the degree of material can be magnetized in a magnetic field is around 10 power to -4. Okay, the susceptibility to the magnetic field is about this value only. It's also considered as low response to the magnetic field. And these are the example of materials. The third type of magnetism is ferromagnetic. And the fourth one is ferrimagnetic. And these are the examples of materials. And they are having the highest degree of a material can be magnetized, which is up to 10 power to 6. We can visualize the atomic dipole for all 4 types of magnetism, okay, based on the applied magnetic field. Okay. First, we look at diamagnetic response. Okay, diamagnetic magnetism. So if there is no applied magnetic field, which is H equal to 0, meaning that absence of external field, okay, there is no atomic dipole exist. Okay, we visualize this as a single atom, and they have no atomic dipole. Okay, in the absence of applied magnetic field, or H equal to 0. But in the presence of a magnetic field, H value, these atomic dipoles are induced. Okay, at the beginning they have no atomic dipoles, but when we apply magnetic field, the atomic dipoles start to develop, and these atomic dipoles are in the opposing direction with the magnetic field. So this is our direction of magnetic field, and this is the direction of atomic dipole. They are opposite to each other for diamagnetic material. While for paramagnetic material, originally, without the applied magnetic field, H equal to 0, the atomic dipoles are in random position. Okay. Once we apply the magnetic field, okay, the H value, okay, all the atomic dipoles will position in an aligned position to the magnetic field. Okay, this is our direction of magnetic field, and the atomic dipole is positioned in the same direction with the applied magnetic field. And for ferromagnetic and ferrimagnetic materials, without the applied magnetic field, they are originally in an aligned position. Okay, so if we apply the magnetic field, there is no change in the position of the atomic dipole. Okay, that's why we call this as ferromagnetic and ferromagnetic materials. Magnetic materials are important in the area of information storage. Okay, magnetic recording in fact has become the universal technology for the storage of electronic information. For example, disk storage media in your computer, either laptop or desktop. Okay, your iPods, your MP3 players, your high definition camcorder hard drives, credit card, debit card, and so on. Okay. Computer bytes, sounds, or visual images in the form of electrical signals are recorded magnetically on very well segments of the magnetic storage medium, either a tape or a disk. Okay, if you can see from this image, this is the SEM TEM image, if I'm not mistaken, the TEM image of the hard disk drive made up from cobalt chromium alloy grains, and these are the recording tape. This is the unknown metal alloy, ferromagnetic metal alloy, and this one is ferrimagnetic barium ferrite particles. Okay, all of these are the TEM images. Final part of the metal application is the materials that exhibit optical properties. Optical property refers to a material's response to exposure to electromagnetic radiation, or normally we use visible light. So how the material or metal responds to the electromagnetic radiation. For a photon of electromagnetic radiation, the dependence of energy on frequency and also velocity and wavelength, as shown in this well-known equation of energy. The radiation of light on a material, it can be either reflected, absorbed, or transmitted. If an electron excited from an occupied state at lower energy level to a vacant and higher energy level, and this is the excitation of this electron from lower to higher energy level is due to the absorption of a photon of energy. Okay, and the amount of energy absorbed is given by this equation with Planck constants value and the frequency of incident light. Once the electron is excited to the higher energy level, this electron, it does not remain in this excited state forever. After a short time, it will fall or decays back into its ground state or unexcited state, and this will re-emit the electromagnetic radiation of the photon will be emitted back. Okay, if we have metal as our material, okay, the energy in terms of photon will emitted from the metal source, and this is called as a reflection of light. We can use these optical properties of materials in various applications. Okay. First, we will be looking at the luminescence phenomenon. Okay. Some materials are capable of absorbing and then re-emit the visible light, and we call this as luminescence. Luminescence is classified according to the magnitude of the delay time between absorption and re-emission. If re-emission occurs for times much less than 1 second, okay, the phenomenon is called as fluorescence. Okay, so normally less than 10 power to negative 8 seconds. If the re-emission occurs for times for a much longer time, okay, larger than 10 power to negative 8 seconds, this phenomenon is called phosphorescence.